So what I was going to do is start with a real top level discussion of what forward is. These are actually essentially slightly updated slides on a presentation, a tutorial I have on the forward webpage. Before I dig into the actual kind of showing you in real time, which always goes perfectly, how to get at some of the data, and because we're going to continue that in the practicum, I'm going to jump out of that part of the talk a little bit about kind of the models behind what we was saying yesterday, and then if we have time, I'll jump back in, and if we don't, we will do the practicum. Let's start here. So what is forward? It is a SolarSoft IDL package. It is designed to synthesize coronal observables, doesn't do chromospheric, although there are some possibilities in there, for example, to model a prominence in absorption, something that Terry Kuchera worked with me to put together, so that is in there. And it uses analytic or numerical physical state models. The power of it as a package is that it can interface directly with a range of existing coronal observations using Virtual Solar Observatory, or we've worked directly with the monolithic web pages to access the data there. We have various other data sources that we directly work with. It's one of the components in an inverse problem or an optimization problem, and it's providing you the three kind of elements. One of them is a means of specifying the physical state. So that's like the density, magnetic field, temperature of the corona in 3 dimensions. Those are the models, right? The analytic models or the numerical models. It has well-defined forward calculations. So for the various lines or wavelengths you're looking at, the kind of thing you do expect of polarimetry, it's got the equations to determine what will generate the observable from the physical state. And it also takes into consideration the observer's position and all the geometry and does all that. So, tries to get a lot of that stuff done in a systematic way. And then, of course, it has access to the observations itself in a way that allows you to kind of put the data right next to the model and look at it. So that's the intention behind it. What it is not doing an inversion. Okay? All it's doing is calculating the forward calculation. So if you want to do an inversion or optimization, or if you want to do some sort of then you can use format forward to give you that piece in your likelihood function or whatever, or you can do some sort of forward thing. All right, there's a lot of codes. I think what's my latest count? This was actually, I wrote this talk a couple of years ago and it said 337 codes, but since then we've actually expanded quite a lot. So there's probably another 50 or 100 or something like that. So there's a lot of codes in here. And this, by the way, before anybody asks, is the reason it is not yet in Python. Just to be clear. Love the idea, a little bit daunting. Okay, and these are, so this is, I can show you how to actually this index so you can see what's going on here. These ones in the middle are the models, okay? And then then this over here, okay, let's talk about the models. Now I understand what I was doing. I was highlighting models and then showing you some examples. So these are physical state models. Again, these are the ways you can specify what the magnetic field of plasma is looking like. We have, for example, structural models, plasma only, that just give you density and temperature. They don't actually do magnetic field. For example, the Poisson model is something which Morgan did. It's kind of, it's like the GSM Dionesian model. It allows you to do a Poisson type shape density distribution for a CME, change various things like the size and so on. It has what is kind of different from the original Poisson type models is it allows for a ride in the axis of the CMEs that goes out, which is quite nice for doing some sorts of analyses. This over here is the Kazmorph model. This is actually the first one, I think, Ula, that we put together. We had an ISI team that started forward back in 2011, and it was to look at cavities. So we put together this morphological model of a cavity, which is essentially kind of a tunnel-like structure in density. With this, you can put a prominence in the middle of it as well. And you can do other things. You can put a hot, chewy nougat of temperatures. Kathy Reeves did some analyses of this in X-ray, for example. We have a tomographic model, which is something, again, Hugh Morgan provided for us, which is a 3-dimensional distribution of densities obtained by, I think it's either stereo or LASCO data, chronograph data, and gets a 3D density, which can be useful because it's based on particular Carrington rotations and give you a density background. Then we have models that are essentially magnetic field. Yeah, go ahead, John, interrupt anytime.
Does a Poisson model contains any velocity information?
The Poisson model, yes, it does have a velocity. It moves out, and I forget exactly how he sets up the relationship to velocity. There is a velocity that you can you can track the CV because it has a function of time. About
Is it a bulk velocity or there is different velocity
the
everywhere?
bulk velocity. Yeah, definitely. So it's fairly simple. And there's magnetic field only. The dipole is kind of like just a real simple dipole. Nice one for testing certain things. It is just a dipole field, but I put in a density by, like, you can choose a parameter for where you want your field lines to close, and anything in that can have a different hydrostatic density than anything above it. So it's just a very, very simple model to kind of test. Maybe you're testing a new observable. The potential field sort of surface model, this is Mark DeRosa's. It plugs into that whole set of codes. Now, I said this is magnetic field only, and I'm showing you dense observables that depend on density. And that's because we've put in these ways of kind of defining the topology, and this opens up some opportunities. For example, the potential field model, you can take these data cubes that Mark DeRosa did, and using Mark DeRosa's field line tracing code, Forward knows how to go in and figure out for every point in the cube of potential field, whether it's on an open or a closed field line. And then it just marks them with a 1 and 0 and resaves them. So you have a cube of magnetic field and density, which allows you to do surprisingly good forward model synthesis of, for example, AIA. This is a potential model, but just by weighting the plasma differently, the open and closed field, you get the coronal hole type structure versus the streamers. So that can be that's like what we're using right now, some of the analyses of the cavities over the solar cycle. Then we have models that are essentially magnetostatic, plasma, magnetic field, but no velocity. These are some of the earlier ones we did. They're analytic. And of course, that's nice because it's super fast. You can do a calculation. These are models that essentially all of them have BC low is the common factor on all of these. These two on the middle and on the right are, what do you call it? Flux rope type models. The middle one is essentially a cylindrical flux rope that he did as an axisymmetric Cartesian, and I kind of kludged it to wrap around the sun so you can make a flux rope tunnel very easily. The lights and low is the original Spiramak implementation for a prominence model that was done back in 1997. And this one that we did also with Fran Bagenal is a nice global model, which is again analytic. And it's nice because it is you have closed and open fields, and you can make it dipolar, or you can add octopolar components to change the complexity. And again, these are quite useful for testing, for test purposes. And then we have ones which have velocity. The Gibson low model is essentially, it came out of the lights and low model, which was a prominence model, but the Gibson low model is one where we it's actually time dependent. And so it's an MHD model of a CME that erupts out in a self-similar fashion. So the velocity there is very special in that it's a self-similar expansion of the structure that was there before, but it is a fully self-consistent solution to the MHD equations. And then, of course, when we start using simulations, we can use all sorts of kinds of simulations. This one is Predictive Science, which is plugged into Forward so that you can just put in a date and it'll go grab PSI's cube for that day, and you can synthesize all sorts of things. Shown here is white light. This is XRT, and then down here we've got Stokes I from comp type observations in the 10747 line, and then this is like a 193. We can do this for any simulation. I think that's the next slide. NumCube, your model here. So any numerical cube we can plug in. We've done it for Matthias's URM, for example. We've done forward synthesis of that. And so there's various options we can do. Okay. So those are the models of the physical state. And then the question is, what can we actually synthesize? We can do white light. And it's interesting, of course, because all of these, each one of these is an interesting thing. You have your plasma sitting there, and then light operates differently you get different kind of physical processes that create the light that you measure in the observable. So for example, Thomson scattering is what you see in the coronagraphs and the heliospheric imagers when you have the photospheric light coming up and scattering on the coronal electrons. So that gives you your white light. And your observables of polarized brightness. You can also take the ratio of that, which gives you a polarization fraction, which is something we're really excited about in Punch because it's a way of diagnosing location of something along your line of sight. In the EUV and soft X-ray, your physical processes are collision-like excitation as well as continuum absorption. Again, like I said, we have a kind of a blocking type thing put in so that you can have a absorption modeled structure in the middle of a emission structure. So we have a way of identifying if you have cold plasma and then creating an absorption type structure. But mostly you're looking at the emission from the collisional excitation. In the visible and IR and in the UV, whoops. Sorry. We've got resonance scattering. We've talked about that this week, as well as collisional excitation. We've got, of course, the polarization, diagnosing the magnetic field, both the Zeeman and the Hanley effect. We've got Doppler shift. We've got Doppler dimming, which is something we've implemented in the ultraviolet lines. And you can observe IQUV, you can observe the velocity, et cetera. And we can talk about any of those processes if you want, but I can, for now, I'm going to move on. Then we've also got radio. We've got thermal Bremsstrahlung modeled, we've got gyro resonance, we've got Faraday rotation, and again, we've got Stokes I, as well as rotation measure, which is the Faraday rotation, which is a diagnostic of the magnetic field. So all of these things are probing different parts of the plasma. And so one of the powers, of course, is to look at them side by side. And if you're doing a likelihood function, if you're trying to optimize, you could take a whole bunch of different observations and synthesize a whole bunch of different types of synthetic observables and optimize using all of them in some combination, which I think is ultimately the most powerful way to go, because these observations probe different parts of the corona, different field strengths, different, whether it's a vector field or a line of sight field or a plane of sky field or direction. And so by combining them, you've got something which is far more powerful for truly diagnosing.
That's a question about
yeah, that's pretty much the first part.
Forward actually does this. Is it like for EUV lines, for instance, is Forward actually do all the calculations there, or is it grabbing the anti-code or something?
Great question. So Terry Kuchera is the one who has really kept things up to date with Chianti. We do need to do an update. I've done a kind of a Band-Aid because Chianti has now pushed a new Chianti where, like, for example, the abundance files, some of the edits I made to Forward in the past few days have been associated with that. Terry is planning to do some updates in the next week. We've got a meeting next week to try and get this up to date.
Fundamentally, is Forward in itself, or is it
fundamentally what's happening is that Terry is generating lookup tables using the latest Chianti, and it pays attention to what Chianti you're using and so on and so forth. So that when you are at a given density and a given temperature and a given height, it's going to the lookup tables rather than doing the full operation of the Chianti, because it makes it faster. So this is why I'm saying I've got a kind of a critical partner in this who is keeping it up to date, but that's how it operates. So it's basically lookup tables for Chianti. Any other questions about the basics? Any of the things I just said? Yeah.
A follow-up question about Chianti. So if we are calculating Stokes I, that's simply from CLE, not Chianti.
If you're using if you're doing the comp type things, it does not use Chianti at all, except I believe in the ion abundances, it's using that, and we've been kind of updating that recently. So we try to make it as consistent as possible with the latest Chianti. But generally speaking, it is in a different path of the program. It is not using the Chianti lookup tables or any of those things that Terry works on. Yeah.
Just curious, for the resonance scattering, which kind of photo redistribution function the resonance scattering?
I don't think I'm going to be able to answer that. I don't know if we have somebody in the room. Maybe Alan? Is Alan with us?
Oh, no, I have to skip it.
Okay, maybe we can come back to that question because I can answer that. Other questions?
The radio includes polarimetry.
That's right. That's right. Yeah, it does. So it has, for example, we can do the Stokes speed from the thermal Bremsstrahlung. There is a circular polarization and get out as a diagnostic for line sight field, which is a very interesting complement to what we can get out with our with our comp type measurement or cosmic type measurement. Yeah. So these are that, and I'll jump ahead to the credits. We've got an original paper, of course, the CLE papers for senior judge. We've got the UV spectrophotometer Zhao did some of the fundamental work there, which of course was based on the fundamental work of Fineschi and others. And then, of course, we've got a lot of Chianti-dependent observations. And that's how you reference it. Oh, I know, it's on this page. This is all the contributors. Stephen White gave us a lot of the radio, for instance, and Tim Bastian as well. So these are our contributors. And we're continuing to grow. Just in the last couple of years, Russell and Tom are pretty recent. SynCom is something that Valmir and YSBL put in, we're working on this summer. Turbulence one with some of Bill Matthews' students, Chicha Picora with Yan Yang. And then Gilly has a Stria code. These are all in development. And then Ravina Khan, who's here, is doing new observables in the EUV spectropolarimetric lines that we're currently testing and putting forward. And I've been doing a lot of stuff with Punch in the wide field. So this is, it constantly gets updated, which is why it's important to update. And let me just for a moment say, for those of you participating in the practicum, at lunchtime, would you mind doing one more update? Of course, just even yesterday, I found some things I wanted to change, but it should be pretty easy and quick to do a fast re-update. And I can troubleshoot at lunch if you need to. So that's the SSW upgrade. It does need to be updated fairly common. And the other thing to point out right now up top is that the CLE, the forward calculation of the comp type lines uses the Fortran code from Phil Judge, and you need to have an up-to-date compiled latest version. So if you have a version from like 10 years ago, it has been changed. It doesn't change nearly as often. So if you do a forward update, the way to tell is just go look into the directory where that is, and I'll show you that in a minute, and see what the date stamps are. And if they're like recent, then you might want to recompile, but otherwise you usually don't need to do that. Any other questions about forward? Yeah.
What's the maximum field?
You can do any field of view you want, all right? I mean, it's limited by your model, your physical state model. So for some of these analytic models, you can do as far as you want, although they become less and less true as you go further out, probably, because they're optimized for the corona. Yeah, there's nothing that limits you because we put in the non-parallel lines of sight. So as you go further away from the sun, it's dealt with appropriately. And the other thing is it can, and I'll show all this later, it can like load up a data set and take from the FITS header, the V angle and central meridian position, and use that Carrington position, use that to then, when it runs like one of the codes, to put it in the same exact observer's position. So it's got a lot of synchronization like that. How much time do I have in this presentation?
It's an hour.
What do I have left right now?
You have 45 minutes left.
Perfect. So I'm going to go into the kind of the science behind this, and then we're going to come back to the forward, and I can show you kind of some stuff that will set us up for this afternoon. So, okay. So, and this is one of the reasons I have this open. Sure. Right notes. Right. So this is an example. I think I already showed. No, I showed a variation of this. So again, this is predictive science model, which is the MOS model, which is the global three-dimensional corona. What we have here is we have different ways of connecting to the magnetic field. We've got the line of sight field from the Zeeman effect. We have the plane of sky direction from the azimuth, and we have magnetic topology from the linear polarization. And let me dig into that a little bit. So let's talk about that linear polarization diagnostic that we've been looking at all week. This is the saturated Hanley regime, which means the Hanley effect is actually a depolarization effect, which both depolarizes and rotates the polarization vector in response to the presence of a magnetic field. And it has a dependency on magnetic field such that if you're in for a particular coronal emission line, if you are in its kind of zone of influence where the magnetic field is at its place. So for example, for Lyman alpha, I think it's about 60 Gauss. So if you have fields kind of around 60 Gauss, then it's going to be able to diagnose them through the way that the linear polarization is depolarized and the polarization vector is rotated. However, for the visible IR lines of COMP and UCoMP, we are in a regime where that crucial magnetic field is like what, 0.01 Gauss or something? It's very small. It's too small to really be of interest in the corona, okay? And so for that reason, we are saturated. And the Hanley effect, it no longer is sensitive to changes in the magnetic field. It gives you a measurement which is only dependent on the direction of the magnetic field in the plane of the sky and the Van Vleck angle, which is, and it's important because it's not just the plane of the sky, it's the angle between the magnetic vector and the local vertical or radial vector. So that's actually 3 dimensions. So the Van Vleck angle is relative to the radial vector, but it doesn't have to be, the field doesn't have to be in the plane of the sky. So you get a strong LRI signal when the B is mostly in the plane of the sky. And so most of this is gray, all right? you go through linear polarizations nulls when the magnetic field is 100% oriented along your line of sight, and when it crosses that Van Vleck angle, which is between B and the radial at 54.7 degrees. So it turns out to be a diagnostic of magnetic topology. It's something Ula said the other day, really was like, yes, exactly, was if we didn't do forward modeling, this would just be a bunch of blotches. You know, I mean, honestly, it's really hard just to look at the linear polarization, this gray image, and say, oh, yes, I know what's happening here. The forward model is really important for really understanding that. This is actually a little easier to interpret. Yeah, go ahead. Who's online?
Richard, go ahead.
Hi, yeah. Is there a way to tell the difference between, so you said the linear polarization is 0 for 2 conditions. Is there a way to tell the difference between the 2 conditions? Like, is there another thing you can use in the data that says whether B is along the line of sight or we're at the Van Vleck angle?
Well, with Cosmo, you can use Stokes field. And that will answer that question in a lovely way, because you'll actually get magnetic field information along the line of sight. That's a good question, though, and I'm wondering if actually the radial azimuth might be something that would answer that question. I don't know. Does anybody have a quick answer? That's something we should think about.
Yeah, but the easiest answer is probably look at the AIA and see the configuration of the field loops and so on. So we see if we have something in the plane of sky or we have in the line of sight, I think.
Yeah, I mean, I think that's right. And that's where the forward modeling, and I'll show the example. Maybe we can come back to that question when I show the specific example of the flux row, because it has both. It has both the Van Vleck angles and that line of sight kind of null. And you can kind of tell if you have some kind of prior information, if you will, of what you think the structure is generally. Why look at AIA? Just look at
And the instrument.
any instrument. UCoMP intensity.
Yeah.
I mean,
Yes.
So, question from Paul?
No, Yemi has a question in the chat.
Oh, I thought somebody over here raised their hand.
I did.
Oh, yeah.
So this was, I don't think Yemi has a microphone. So she's asking.
No, I
great.
sorry, I changed computers today, so yes, I do. Yes, so I was wondering, so as someone that only really thinks of I, so just to clear up the ambiguity, so the comp observation or the figure that you're showing there, the places where it's bright, it's white, is either where that B field is strong or it's directed in a particular direction on the plane of the sky. Where the magnetic field is not weak. Yeah.
So that's a really important point. It has no sensitivity to the strength of the magnetic field at all. So that's because it's in the saturated regime. It was in the unsaturated regime, and some of the ultraviolet lines like Lyman alpha, for instance, have this capability. It has no sensitivity to magnetic field strength at all. It's only about the direction. And so it's gray. If there were no magnetic field or the magnetic field was 100% radial, for example, it would just be gray everywhere. But as that magnetic field direction crosses these critical angles, either the Van Vleck angle or the becoming oriented along the line of sight, it drops into a linear polarization null or where it goes dark. And the interesting thing is it happens pretty fast, right? It's a very sharp transition. And so the smearing you're seeing are line of sight effects, really. And so you really don't have information except at those critical points. Yes, I mean,
There's gonna be
This is a lot. Right.
and that's a lot of flux. Yeah.
So the follow-up point you need to point to its weight is normal to those directions, right? So
No, it's anything other than those directions. It's really not sensitive. There's not like a smooth gradient between it. It's kind of like when you go to the line of sight, it just suddenly goes dark. When you cross the Van Vleck, it goes dark. I mean, we can look at it's pretty abrupt. So really where it's gray, you've got no information. In this plot, you have more information in the next plot. So let me show it to you.
Can I add something?
When is that? It's not really.
I'm sorry.
Yeah.
Jenna and then Ula.
There was a discussion at Shine about this issue of the field strength and the weak field regime, and that I thought was pretty interesting because I always just took that for granted before, and I didn't totally understand it in the session. So I had to ask it again, and I hope it's not too much of a tangent. But if you have like a pixel that had a 0.001 one pixel where your field was really weak and it was in the regime where the Hanley effect was sensitive to magnetic field, what would you expect to see at that pixel? It's not just a measurement of the angle now, or is that not a meaningful question?
So
I think it's 10 to the minus 5.
it's really,
Okay.
but it's a null.
But it's something.
So you'll see it, the nulls do show up, as, yeah, that's a really good question. And I have a slide that can answer that,
Okay.
but, maybe let me get through this first.
Yeah, that's
Because what we did was we did a thing where we basically changed the field, through like, we let it go. I forget if we let it go. We actually did it for the ultraviolet line. We like saturated it. We let it go up to like whatever it needed to saturate, like 100 or 1,000 Gauss or something. And you can see how the vectors change and the line of sight changes. So what happens is, if it gets to very weak field and it's oriented along the line of sight, your azimuth direction, the angle of the polarization vector will diagnose directly that strength in that point. But the problem is if that happens, odds are you're going to have plasma along your line of sight where it's not true. And that's going to wipe that signal.
Yeah, okay, because you're measuring an integrated line of sight, so it's kind of meaningless to
Yeah.
have like a 0.00. Okay.
Yeah. And these values, as Juliana said, they're not exactly zero. But again, you've got plasma along the line of sight. You're not expecting something. I'll show you some examples of when we take like a plane of sky cut and then it's exactly zero.
Okay.
But when you're looking at any kind of observations, it will never get to zero in terms of the polarization quantity. And the field strength might get really, really small in a localized area. But in terms of the linear polarization signal, I think you're going to be dominated then by the rest. But I think it'd be fun to look at that.
Okay.
Yeah.
Okay.
So we have, I think.
Yeah,
and then-
I just want to add something to the first question, because how to recognize if we have Van Vleck or plasma directed along the line of sight. We can look at the direction of the linear polarization, because if we have
I was going to say, we better just bring this up. Yeah.
yeah, if we have the angle, if we have plasma outside this structure, the direction of the linear polarization is along the same as direction of the magnetic fields. But if we are inside this angle, it starts to be perpendicular to the direction of the magnetic field. Yes.
That's right. Yep. So you know when you're inside. So yeah, actually, let's walk through this slide because this is an important
Still
slide.
more questions?
Yeah.
Probably a name question to correct me if I was wrong, because in my memory that even if you don't have magnetic field, the scattering will naturally create some polarization. So even if your magnetic field is along line of sight, I think the linear polarization is not exactly zero. I don't know, but
So it's a depolarizing effect. So yes, exactly. You start, if you don't have any magnetic field at all, you start with a gray everywhere. But when the magnetic field is, if you have all your magnetic field, in fact, let's look at it here. If your magnetic field is along the line of sight, then you will get a depolarization. You will get the linear polarization in this saturated regime, right?
okay.
You will get a depolarization. So that's what I'm showing you. This is a fluxo. This is UCoMP simulation, okay? And you're looking through it. And here's a cross section. And here is that fluxo axis. So it's 100% along your line of sight. And you can see that the linear polarization, the forward model, is exactly zero right there with a fairly sharp, even though this is a smoothly winding flux rope, right? So it's the twist is kind of approaching the axial field very smoothly. It's a very sudden dot right in the center where the field crosses that angle where it's mostly along the line of sight. And we should think about your question. It's a good question, exactly what's happening to cause that depolarization in the saturated regime. Depolarization of the Hanley effect is in the unsaturated regime. Yeah, Momo.
Is there a 3D integration of one line of sight?
No, not yet. So we start with just a slice, just to kind of make the point. And then these guys are the Van Vleck angles. And what's interesting is people like say V for Van Vleck, right? So if you didn't have any sort of here along the neutral line of that, this is the flux or cavity type system, right? Where the magnetic field is along your line of sight. If it was fully planar, your linear polarization would essentially be gray, but you would still have the Van Vleck little line, and it would look like this V. It would actually, this V here would come to a point down at the sun, because you'd have an arcade of field and plane of sky. And every time you crossed 54 degrees, you get this linear polarization null like that. It would come down here. This kind of structure in here is because we do have a flux rope. and it's distorting the field direction. So you can see this is kind of like are you guys seeing my mouse? Yeah. So this is like a, actually, this one's so cool. Let's see if I can do it. Aha. You see my laser pointer now? Okay. So this out here is like an arcade-like field. So when the Van Vleck angle here is showing up, because that's when that arcade-like field is 54 degrees. You get into a flux rope and now you have these circular cross sections. So the field's kind of getting bent. And so that's bending the Van Vleck angle like this. Okay. And then right at the center, you have this other effect, which is the line of sight field, which is giving you this dot. And then with this picture, yeah, so there's Van Vleck in the flux rope. And actually, let me go back. This is, I guess I'm not showing the one which kind of shows what this looks like. Oh yeah, no, it does. You take this picture and now you integrate a curved flux rope, this particular model, along your line of sight, and that's where you get your lagomorph. And the direction, the azimuth, which I'll go back and show you, can be seen. We see it in those red blue plots, which are a way of showing like whether you're you're tilted toward or away from the radial. But you can also make polarization vectors. That's what these little green lines are. Okay. And the little green lines are showing you, this is the model on the left. So we've taken this flux rope, we've synthesized linear polarization degree, or L over I, which is the black, which has the rabbit ears and the rabbit head. The rabbit ears are because of the Van Vleck and that kind of overlying arcade. The rabbit head is a combination of the in line of sight effects of the Van Vleck angle kind of in this part of the rope and that central dot linear line of sight field, which also changes a little bit as it curves, right? Your line of sight will change a little bit. So it'll kind of smear it out in a way that's not because of a sensitivity to the field approaching the line of sight, but because your line of sight plasma along your line of sight is picking it up at different places. Okay. So you smear it out and that gives you this rabbit's head. And then the direction of the linear polarization when you're outside the Van Vleck angle is actually tracing the direction of the field beautifully, right? And this is what Ulu was saying. The amplitude, by the way, of these green vectors is tied to that linear polarization. So you can actually see how it decreases as it approaches the Van Vleck convergence. And then right where it should be kind of coming over like this, it flips 90 degrees. And that's this ambiguity in Van Vleck angle. And then you cross it again and it flips again. And this is how the information of that, if you're looking at something you kind of know you've got an arcade and you see this dark region here, you're like, oh, that's a Van Vleck conversion. If you're looking at something and it's a cavity and it's got a neutral line that's oriented along your line of sight and you see the dark region in here, you can speculate it's because of that twisted field, that sheared field, axial field component in combination with the Van Vleck angle. And then these are the data. And I just want to point out how well it matches, right? See, it's getting bent over as it's going along that arcade. It has the inversion, and Hulu's got better versions now. And then you go here, and it crosses, and so on. So really, that kind of structural thing, it matches.
So when you compare the flux rope with the Cherokee without the flux of analysis, since we are occluding the lower part, how different are really in the polar model? Because many of the things we observe in linear polarization, they really look more like two diagonal straight line with something noisy close to the dark under there. So it's not very clear to me that I can say there is a structure there that is either an arcade or a flux rope. It's not obvious to me that I can distinguish between the two. So
without getting into the kind of the whole flux rope versus shared arcade in too great a detail, it really depends on the shared arcade model. A lot of shared arcade models that are modeling the shear of the prominence. The prominence is way down here, okay, under our occultedness. Shear, the line of sight kind of axial part of that is down here. And so they won't get this structure up here at the heights that you see the cavity. There are probably large sheared structures that you could create that would give you something like that in this part up here. I think I have a picture later to really distinguish between something where it's got a circular cross section, right? So you could have something which is just sheared and really high shear up in the cavity that might give you something that looks a bit like this lagomorph. If you can observe, and UCoMP is letting us see a structure go high enough up that you can observe the whole circle, that's when you start to see the differences, because that circular cross section, which is unique to the flux rope, will give you a different behavior below the center of it than something
So
which
you
is
need to
like
see the
a.
axis above the occulter at a level which you have a good signal or something like that?
Yes, the ideal is you would see your axis well enough above the occulter that you're seeing the lower part, if it's a flux rope, of the flux rope, and then you can distinguish, yeah,
Something.
sure.
We do not have only observation linear polarization. At the same time, we have Doppler velocity.
You know, in fact,
But
yeah,
all that
that's
structure,
Yeah.
it's hard to believe that we start to see shared arcade and not the flux.
I agree 100%. It seems to me that a much stronger indication of a flux rope, at least in the UCoMP observation,
It is the circular
is the
velocity.
velocity signal, because that is consistent with some kind of
Yeah.
flux rope. Why I have at times looking at linear polarization and say, like you see, this is a flux rope versus
Yeah.
a
The problem is it's kind of squished
Exactly.
down, so you get your nice little circular cross sections, but what the linear polarization is looking like there is just a big dark splotch, so it's a little bit hard, but if it gets higher up and you start to get something that looks like an X, that means it's that, I mean, you can see it here. Here, where's 54 degrees? It'd be like here, like this, and does it show it? I have to get a little bit higher up. You get situations where you get it like this and then like this, if the center of the flux rope goes high enough.
I just want to make another comment. So not only do we have all this information, we also, when we do the wave tracking, and see how I can comment on this, we determine the direction of propagation of the waves. And when you correlate that with the direction of the plane of sky azimuth, they correlate really well, except there are places where they're off by 90 degrees. So the wave tracking is additional information that will allow you to identify those places where you're inside the V there, where the field is 90 degrees to the actual magnetic field. So there's even more information that is available.
And I think that answers the earlier question. If you have a linear crossing at a place where you see the direction of the Stokes vector stop being parallel to the direction of the wave propagation, then that dark region is unflexible. If there's no evidence of that, then it would be a line of sight, except if it's most all along the line of sight, what's that going to do to your waves?
Yeah, actually, when I'm comparing the UCoMP wave tracking, wave angle, and the UCoMP and linear azimuth from linear polarization with models like PSI, and I found it's not actually exactly corresponding to the exact plane of sky. There is still a line of sight integration effect, even if you are starting from the azimuth or from the wave tracking angle. They are not the exact direction on the plane of sky.
Yeah, that makes sense because it is a weighted, plasma weighted. And one of the reasons I like working with cavities is because you've got this reinforcement along the line of sight, which makes it easier to interpret for the
Yeah.
structure.
Yeah, so cavity, I think, because you have a rather standalone structure along the line of sight, so it should be more.
We should study that. We should study some cavities and see how that, like specific to the cavities, if it's how those things track.
Yeah, I think for a model like this, you should expect this kind of correspondency. But what if there's other structures along the line of sight?
It'll blur it, which is why, as I said, I like the cavities, which are like the long polar crowns,
Yes.
where essentially the only thing in your line of sight is cavity. So you get some curvature effects, but you don't get like other stuff in the way. But yeah, if you're looking at an active region, it's a more complicated problem to interpret.
And so you can see like the difference between the accompanying disk and the limb of the sun. I'm assuming it's in yellow there, right?
Yeah.
Like, so you could run the model all the way down to the limb, and it looks to me like there would be interesting things to see down there. I wonder if that would be a good argument for either one day getting smaller accompanying disk, or is there something you can do during an eclipse to look at how this?
It is a great question. And anybody who knows me has worked on a mission with me will know that I'm always being slower the occulting disk, lower the occulting disk. And I use ULA's data to like back me up because she's done all this analyses of like the heights of cavities and everything. But eclipses, wow. Yeah.
Yeah, linear polarization during an eclipse to look down low would be neat.
I might,
You need to get lucky and have the structure at the right place during the eclipse times, but
if it's the right time of the solar cycle, I don't know, odds are good you'll have a cavity.
It's tough for us to lower, we can't just arbitrarily lower the occulting. I mean, there's some blurring and there's seeing and
And
stuff
another
where-
is pointing too. I mean, we had better pointing, but it's hard to.
pointing,
I mean,
seeing.
we already get spillage sometimes because the pointing is never perfect. And if we lower the pointing this even more, then you throw out a lot of data because you get saturation, and so it's, you know, it's hard to do it. I mean, it's more.
Got one more thing for April.
I mean, in space, I think you're more.
But if we could do it with the eclipse, so Ula showed, I just want to
I
say,
have a question for both of you, sorry, because I'm really interested in this. I found only one case in pseudoswimmer where the plane of the type of that particular structure was basically almost identical to the line of sight. We don't planner. And I could see that field that was perpendicular to the line of, I mean, was perpendicular to the plane of the sky. It is so dark. And I had one example when I saw that dark dot. Have you ever seen a cavity? When you have that dot in the middle that is perfectly aligned, so you don't have this blowing effect of this.
so this is related to what you did with the changing the angle, right? And I just wanted to say, just because it's relevant to this, Ula showed an example of what happens if she changed the angle. And she was showing it, and if you look at this structure, this is a slice. When you integrate it, and you're above the occulter, it looks like this. When you integrate it and you look down to, if you pretend you don't have an occulter and it's clips, you'll get something which has got kind of an X shape. You can kind of see that here, but the problem is you haven't got the curvature in the other lines of sight. You end up with something which is kind of like this with the head in the middle. And Ula had examples though, when you get certain orientations, that dot kind of pops, right? And that's the only thing. You don't see the big head of the bunny, but just that little dot. And I think it might be because we need to go back and look at that analysis. And I think you did it at the equator. There's all sorts of geometric effects. If you start going up, as I said, the preferred thing is great circles. So if you're up at a higher latitude, actually the orientation is perfect, is it's oriented kind of like along a pie slice, a radial slice. But at the equator, you can just put it like that. And I think that's what you did. But there's also, you can change the neutral line orientation in Yuhan's model. And
Did you see the observation? Because I saw only once the pseudoswimmer, it felt that really
we
was.
should probably go to pseudoscripts.
I mean, have you ever seen it with the cavity?
Well, in a pseudoscript, yes. It depends what you mean by that.
before we move on, I don't know, Jenna might have wanted to say.
Yeah,
something
Jenna.
about the
Another
eclipse.
point about to go back to your clips. Can you do this with the Polcam if you added a filter? Like maybe one of Hashing's really narrow filters for the.
I mean, it depends on the spatial resolution you need. In principle, yes.
Yeah.
These are big. No, maybe not the top though.
The quantum efficiency is at the whole cam we have at 1074.
Pretty poor.
Oh, yeah, you need.
The one we have,
You
but
have to order.
you need a
yeah,
higher
but
filter.
they're starting to make better versions of these and ones with better resolution as well.
Okay.
That's yeah.
What came up, if you have money, you got that ready.
Yeah.
If you have the money, you can tell them to make a mask for, like an in-gas detector.
Yeah.
And they'll make an near IR.
So if I
Whole
can,
count, but I don't know how much.
so
that
if you don't mind, let me get back to the talk because we're getting to the point that the questions are asking things that get answered in earlier slides. So, and let's show that later, guys. Let's go back to the talk.
And we have a practicum this afternoon
Exactly.
of 2 hours where Sarah can follow up on all that
How
stuff as
to do
well. I'm just.
So, yeah, I have to be far ahead. I just wanted to show this because this is two ways of looking at that line of that azimuth plot. I already showed you those green vectors, right? And this is just showing you what the blue and red plots that we show. And we like the reason I'm a big fan of the radial azimuth as opposed to the azimuth product is the azimuth product is dominated by the color wheel, which is dependent on the instruments, the way the polarizers are set up. So it's not anything physical to the sun itself. When you convert to the radial of the frame of reference of the local vertical, the instrument's gone. You're showing something where the colors are showing nothing except for the way the magnetic field has affected the linear polarization signal. So in this case, if it's tilting, if it's blue, it's tilting clockwise. If it's red, it's tilting counterclockwise. And you can see how this lets you get like diverging fields look like this. And they tend to have this sort of structure, blue with kind of a blurry black in the middle to red. Whereas converging structures look like this, because what's happening is they're hitting an event flat and they're bending around and then flip, they're going 90 degrees to the bend. So, I think it's good to keep in mind. Yeah.
And I'd like us also to produce a superposition of that with the white light, with the intensity from 1074. So it's illuminates. You see exactly what you'd expect under that. It's almost dead center in the cavity.
Yeah.
So I think it's a nice additional quick look data product.
Yeah, this is information about the non-radial expansion of the corona, like here, which is also seen in white light when you do.
But I actually meant the 1074 intensity.
Oh, yeah. Oh, yeah.
I can't go on the same white line. I mean,
But any kind of intensity is sometimes in type structures, but the benefit is this kind of gives it to you in a more quantitative way, right? Because you see mostly boundaries when you're looking at an emission, right? If you're looking at intensity, you'll see like the non-radial structure, but you're seeing it at those boundaries, those edges of the flow structure. Here we're, it's the extent we have signal, we're measuring it smoothly in the kind of the diverging field region, which is super interesting, I think. And then this is examples of when you forward model predictive science, and I'm going to zoom in. This is an example of on the left is the linear polarization. So all these dark linear features you see now have to do with that, those crossings, right? And then the red and the blue has to do with the tilt, the magnetic field. And we've got observations on top, and we've got data other way around. Yeah, model below. Yeah. And it does really pretty good, right? I mean, structurally it's matching quite a lot. But if I were to go back here and if we zoomed in, you'd see, for example, it completely misses the lagomorph up here in the upper quadrant. So there's a dark lagomorph, but it's not there. And the reason is because the predictive science class model is not a energized coronal model. It is basically a line of sight magnetic field boundary condition. It has a nice realistic upper boundary condition of the solar wind, but it doesn't have the currents that are in the corona kind of modeled in that way. There's other ways to do that. You have to add currents. But so it's something to always bear in mind when you're comparing, doing the forward modeling, is what is your model really giving you? And maybe what it can give you, and I've got a slide if we get to it, is a difference, and you can find out where it's missing is interesting because it's where it's energized, right? And this is something that Marcel Cortado has worked on. So I might get that. Okay, here are the sort of the three poster child ones. There's a flux rope, lagomorphs, pseudostreamers, and magnetic nulls. Here's the magnetic null, by the way. This is where it shows up. And the question is, should it be bright? And I think we talked about how there might be something that would, because you're starting to get to very low depths, that I remember having this conversation with Bill and Roberto, and I can't remember what, but I think we should talk about it this afternoon.
Okay.
And then this is the how beautifully it gets that divergence, right? Of the magnetic direction, so expansion. And this is it, yeah.
I just wanted to make a comment about the bent leg point versus the line of sight case. The two are fundamentally different because in the line of sight case, it's really it's really like an observer effect. The fact that you are located along the line of sight is what causes the appearance of zero polarization. In the bent leg case, the magnetic field, there it's more of a relationship between the direction of polarization, which is along the outward radial. That's where the photons are impacting the wave function of the transition. And the magnetic field, by being at that angle, it deforms the transition such that it no longer appears polarized. So that's like an intrinsic. It's intrinsically even if you were to look at that point from any direction,
yeah,
it would always be zero. It would always, because the way that photons are, because of the polarization of the transition.
That's a really important point, and it answers it's one way of answering that question is if you were to change if you did have an L5 or if you had another vantage, you could immediately tell.
It would still look like zero.
Yeah, for the bent flag.
For that specific angle. Whereas with the line of sight, once you're away from the line of sight, you start seeing this type polarization. But I don't know. Yeah, I thought about this for like a long time, and that's the explanation I've told myself. But there's different ways. There are some ways, but I think that's one of the reasons. And then you have to imagine the magnetic field almost like acting on the wave function of the transition. It changes how the photons are hitting this object.
Yep.
Yeah, and
And then the same kind of idea would then apply to why you have Hahn effect as the magnetic field strength increases and becomes more and more until eventually it reaches saturation point. And at which point moving the field simply realigns the atoms. So then when they get bombarded by the photons, they're just in a slightly different position. That's how I think about the geometric. Then linear polarization has this very geometric representation. Show what exactly does that correspond to.
Yeah.
The actual atomic transition. I've never been able to prove this. And but I would like to, I was hoping one day that somebody could make a intuitive visible one. You know how they draw those orbitals?
Yeah.
You guys, when they show quantum mechanical states and they say the P1 orbital has this, it's spatial structure, a spatial representation of the wave. I'm wondering how those spatial representations can work together to give us a more intuitive understanding of where the polarization comes from. But I've never, like I said,
No, I think that's great. And if I have time, I'll show, I have a movie where you can see it saturating, which I think is actually helpful kind of see how it goes, but not at the atomic levels, just how the effect on the polarization.
there's like an older explanation in terms of oscillating springs.
Yes.
And that's a 1977 house paper. I think if somebody wanted to.
I probably have that diagram on this other
Sorry,
side.
go
So,
ahead.
yeah.
I'm sorry. That's
No, I think this is really important. Let me go back to the cavities real quick and why we care about them. How long did that time?
10 minutes, 11 minutes.
So this is a nice one. This is what we talked about for the CME. This particular activation of the cavity interruption took 48 hours. So you'd have time then to start the observing thing. And kind of, let's show you it again. You know, if you start to see this and you put you look at this in UCoMP, you could watch this entire structure. And as I said, you'd start to see that X-line, you'd start to see this thing rise and you see the structure go below it, which is unmistakably a flux rock. So I would love to get that. And Lula has one that she can show in a minute, which is looking like it might be showing us that behavior. And this is just a flux, like sort of how it changes as it rotates and how those flux surfaces in your line of sight are going to give you the circular structure, which maybe is what we're seeing in those flows. This is the snapshots of that same one, just to kind of prove that it went from 2012 514 to 2012 516 before it really erupted. It was already starting to get. There's a paper which I probably, we already saw this. Probably have in here. Ula showed this already. These are just seen them all. I'm going to skip through some of this. Already talked about this. All right, so we're getting the pseudostring. I just want to make the comment somewhere. I have it. Brent Forlin et al. Has a paper where he studied like over 100 cavities and showed a correlation between the narrowness of the cavity, the more teardrop shaped cavity it is, the more likely it's going to erupt within 24 hours. And it was a very strong, it was like 80% of teardrop. He did both morphologies and just aspect ratio. Aspect ratio has no, what's what I'm looking for? It's the word where it's like subjective, no subjective thing. But he also just went through and said, looking at it doesn't look like a teardrop. And he subjectively identified them as half domes, sort of ellipses or teardrops. When he did it that way, he got 80% of the teardrops erupted within 24 hours. And it was 10% of the half domes. And it was like in between 20 or 30% for the, so there, it's a pretty strong, and then the same behavior was seen in the aspect ratio as well, but not quite as strong as when you actually look and look for structures that look like this one, which is the only time I've ever literally bet on something erupting. I won. It was when I saw that. Okay, so I wanted to make sure we got a chance to talk about pseudostreamers because that's another thing that UCoMP really sees beautifully. This was a wonderful thing that Laurel Acknell and Chloe Glenot et al. Did this. This was the evolution of the South Pole during the polar reversal in 2015. Okay, so it's the South Pole, and here is a polar crown filament. Polar crown, neutral line that basically goes like this with a nice crown. It's literally a crown. And it was very well formed, and you could see it has this magnetic geometry down here, right? And you notice there's coronal hole, polar hole is blue. It's, I don't know if it's outward or inward, but it's not the same as on the other side of this host region. So what happens is that crown sort of shrinks to a fez over the course of about 8 months and becomes a pseudostreamer. And a pseudostreamer is something with two lobes, but instead of two lobes separated by the other polarity field, it's two lobes where it's completely surrounded by one polarity, right? So that's the definition of the topology of a pseudostreamer. And it was cool because this observation demonstrated how it could actually form at a south pole slowly. And you notice it shrinks to the point, it disappears, and now polar field has reversed. It's something that Mei Zhang looked at as well with BC Low about how the coronal magnetic field will reverse sign before it does its photosphere, which is kind of cool. So that's polar crown, that's the polar fez. And this is what it looks like in linear polarization. So we don't have any flux up here, right? So we don't have the rabbit head is not here. This is all straight up nothing but the Van Vleck angle at the 54 degrees, which is giving you this linear feature, this linear feature, this linear feature, this linear feature, right? And this was the observation during that time period that Chloe was doing these analyses with the swap UV observations. You notice there was actually a polar crown. So this is a model with no flux rope, but there was a cavity and there is line of sight field, shear field. So there probably is a flux rope right here. Now, as you go to that, this is the topology. This is the kind of classic supersymmetric, what you would expect. We need to go back and look at why this is bright because it may be related to what we're talking about, but I have to look at it. Although the thing is that in the CLE code, there's nothing, I don't think it has the capability to do the unsaturated only effects. So yeah, we have to be careful about that. And this is what we observed. Okay, so we saw that kind of nice structure. So yeah, so this is the pseudostreamer, the observation, this is the forward model, and this is the magnetic topology. So these little kind of structures show up. We've got some beautiful cases we can look at this afternoon. Here's one which is a little more lopsided, but it's still a pseudostreamer, and it takes a minute to kind of see how you've got these two lobes with the middle lobe and how that maps here. And this is what I wanted to show Juliana. This black dot that we see in the middle of a pseudostreamer, that's not a null point, or that is, but it is, I think, related to the cavity that was, see this balloon of a cavity that's in the lobe.
This is the axis, that dot.
I think it's the bunny head, but it's been kind of squeezed into a pseudostreamer. So you take something with a lagmorph, and then instead of being kind of open like this, and instead of having that kind of thing, it's surrounded by a completely different magnetic topology. You've put your little flux rope in here. The rabbit's ears are not going to be the same.
But you do have a cavity in there.
But you do have a cavity, so I think
it corresponds to the axis.
I think it corresponds to the axis and the Van Vleck crossings inside the flux rope that's in that cavity. So it's a combination, right? And it's probably not resolved. How much of that is right at the axis and how much of it is because of Van Vleck convergence inside this magnetic structure? I think you need to have higher resolution to tell. But it's okay. We're just about done anyway. So any questions about pseudos? Oh, this is just kind of a cool thing you can do. This is something that Nishu Karna did. We took the potential field for that day and we said, okay, and the potential field will not get your flux rope by definition, no currents. But a potential field is perfectly capable of getting a pseudostreamer magnetic topology, right? That's fine. And in fact, that's what this picture is showing. I think these are, down here, we're looking at magnetic field lines, not Stokes vectors, magnetic field lines in the potential model. And this green is a closed field structure, and this stuff is above it open and unipolar, okay? And this is the potential field magnetic field strengths. You see it has a magnetic null that is right here at the top of its closed field. So the magnetic null in the potential field model is where my cursor is. The star is showing you where for comp side, right? And so what we realized was one of the things that an energized corona does is push, and especially remember that big fat flux rope cavity sitting under there, which is not in the potential model, is it pushes the null point higher. And so by comparing what we observe here, this null, this kind of intersection of lobes, we can compare that to what a potential field shows, and we get a sense of how non-potential the region is. And so what Nishu did was she put a flux rope in where that cavity was and pushed that null point up and matched the actual observations and got it to erupt, which it did. So he energized the corona enough, it erupts. Okay, so that's basically it. The last thing I have here, I think, is Marcel's. He did differences between a potential field forward modeled linear polarization and circular polarization looking forward to Cosmo, and asked the question, if I could difference what if I take a potential field boundary and I extrapolate a potential field model in a region, and I synthesize comp using forward, and I compare it to the observations of comp, the regions where they differ are the regions where it's no potential. And so he created these, you know, they've got a bunny ear kind of structure, right? These structures that are a sign of the non-potentiality that's actually visible even in the linear polarization. When you start doing the circular polarization, it's just pops, which makes sense because in these cavities, you're looking at line of sight field. But even the linear polarization had a measurable thing, and he created this non-potentiality index where he showed how it changed as this structure kind of got emerged. And you can see that it actually, the increase of it as more and more twist gets put into the corona is measurable in the linear polarization. And is measurable in the circular polarization in a way which is actually quantitative. You could use this number to get out how much magnetic energy is there, which is why we want Cosmo. But you could say, oh, look, I am energizing my corona as I'm moving this structure out. And we've talked about using, I think UCoMP is going to be great for doing some like solar cycle studies of this kind of thing and seeing how the energization changes as throughout the solar cycle and how well it diagnoses non-potentiality in active regions, which have more line of sight effects. And we could use the PSI model or well, we need to use energized model to really do this. But yeah, that's one of the things he was working on, was looking at the model which uses Anthony Yates' energized coronal model, which was done in conjunction with PSI as the thing to forward model and compare. And I think that's it, other than just optimization and how we can use it.
Perfect timing. I'll just click. Nice. Great questions. Does anybody have a short question or two?
I've got a short question. I don't know if it's going to be a short answer though. So go ahead. Okay, so it's a general question about forward, not so I take a model and I generate the synthetic observables, and then I go and look at my observation and I see, okay, they don't look anything like whatever. You said forward is not an inversion routine, but does it allow me to go back to that model and play around with things to try and better match my observation?
Every inversion needs a forward model, right? And then you just iterate, right? I mean, you can't have an inversion without forward model.
Sure.
Yeah, you know, the last slide I had up, the DocFM, that was what we were trying to do, but you need external codes. So Kevin Donlas came up with some ways of working with Antonia Savcheva and Nisha and others to do exactly what you said, essentially the forward model. He came up with a whole structure of like how to, you need some sort of something you can vary. In this case, it was parameters of how much axial field and toroidal field in an inserted flux row. And you just, you basically, you solve the optimization problem, constantly adding currents in response to how that difference is. And so, but it has to be a code that's calling forward, not, you have to write your own code to do it, bottom line. And somebody has a hand up.
Yeah, Judith is the next question.
So 3 quick questions. One is that you said that the corona changes faster than the photospheric magnetic field.
Oh, yeah.
How do you know that?
So this was, okay, so this is, it really requires a picture to answer, but essentially what it is it's that polar crown turning into a polar fez. So you've got, if I get this right, and maybe I've got it backwards, that's why I want to think it through. So you have a polar coronal hole, let's say that's positive, right? As it shrinks, it's going to change to negative field, open field at the poles, right? But the open field is not going to be connected to the photosphere until the fez itself shrinks and disappears. And so the polar reversal, you're going to have kind of mixed polarity, and then you're not going to get to the opposite sign open field at the poles until that crown has completely shrinked and disappeared and has been replaced by open field. So it's over
Can I ask,
months. Yeah,
discuss
let's talk
this
to-
more
let's talk
during
to
the
break.
break
Let's talk
now
break.
and should he?
Oh, yeah, she had short questions.
And not-
No, we're on break right now. So
Okay.
Okay.
Ben. And so we're gonna break until 8:20.
Was there a question? I can answer a question.
Yes, go ahead.
And I'll just read it.
Okay, quick question, Sarah. So do you think that we can see any signatures of interchange reconnection in from the closed and open field lines, either in UCoMP or in forward by combining them?
You know, I don't, actually that paper that was, who did that paper? With the current sheet and the turbulence and the current sheet, I know who it is. Brian French and Phil Judge. So the question is, if you had enough resolution, could you see dynamic events? And I mean, that's not quite what you're talking about. You're not talking about interchange reconnection, but it was like little reconnection magnetic islands in the current sheet.
Right.
So given the right resolution, and again, maybe this means Cosmo, maybe it means DKIS.
Mhm.
Yeah, but you need resolution to see that.
That was
Yes.
also a new current sheet following a really fast mass ejection. So it was very strong.
Yeah.
And
Okay.